Hello everyone, the problem that we're looking at today is actually quite good. It's the 2018 US Open Gold Problem 3 of Talent Show. The problem title doesn't really give you much because it's 2018 US Open and it's not even platinum. However, back in the good old days, US Open was actually quite hard and it's quite a bit harder than usual, so that's why this problem actually utilizes a very unique trick that I haven't really seen anywhere else, which, by the way, this means that this is highly likely to appear on the 2026 contest because remember how last time when I grinded the 2018 silver problem, the exact same algorithm was used in the 2025 January? Well, I have a feeling that this algorithm, considering how unique it is, how old it is, and how hard it is, this is like definitely appearable in 2026 January and February contest. Anyways, Farmer John has N cows, and he needs to. Each cow has two coefficients, A. Hold up, W and T. T is how talented it is. W is how heavy it is. So we have to select a bunch of cows such that their weight is at least W, and their talent to weight ratio is the largest. And you have at most 250 cows. A classic n squared time complexity, but the weight limit is 1000, and the weight is at most 10 to the 6, along with talent being 1000. So you can pause the video first and think about this yourself, which is going to be quite hard. Okay, so there is really no good way to do this unless you just know how to do this. The algorithm used is called 0-1 fractional programming, which is basically a type of fractional programming, but you only choose between 0 and 1. It's kind of like 0-1 knapsack, if you know what that is. 0-1 just means that there's only two possibilities for each element. You choose it or you don't. In this case, we basically want to binary search because there's really no other better way to do this, as we don't really know what to choose at all. There is a ratio involved, but we also need to fulfill a weight. So 0-1 fractional programming is designed specifically for this. This is very smart, so whoever thought of this, or to them. The general solution is binary search because you realize that there's a rounding down. Simply doing greedy on those singular ones with highest of ratio is not necessarily optimal, and also we need to fulfill a weight, so binary search admit as the answer. And then we have this equation, the sigma of A, which I use A instead of talent T because I use T for other stuff, and B instead of W because there is already a W in the problem and I don't like capitalizing. Anyways, we have sigma of A times CHI, which means whether we choose I, and CHI whether we choose I. So yeah, obviously sigma of that has to be greater than or equal to mid. However, simply manipulating the equation, moving this term to the right, and then subtracting the mid times sigma bi times CHI term to the left, we get this, and then combine the sigma, we get this, which is very much interesting because now if you think about it, basically we have every single element independent of each other. We just need to figure out whether we choose it by seeing if this is optimal. Whether choosing this is going to be greater than or equal to 0. If it is, then we choose it. And if in the end we can have at most WA, this mid works. And now there's the general case, because at first we considered the cases ignoring the W. We have to maximize the sum of a value, but we also have to satisfy the constraint on another value. This is not monotone stack because, well, this description kind of fits monotone stack, but this is knapsack DP. So yeah, the 0-1 kind of applies to both because we're doing 0-1 fractional programming and the 0-1 knapsack DP. Or wait, actually, I'm not sure. Maybe it's called 0-1 fractional programming because there's knapsack DP involved. I don't know, but you just have to memorize this combo of binary search, a little bit of math, manipulating equation, and then DP. That's the combo for these kind of problems. And then let's look at my code. We have check, which is the check function for the binary search, obviously with binary search from L to R. And then when we do knapsack, there's a tiny trick because the weight can be, as we saw, almost a million. We don't want to go to a million. Knapsack is n squared. We at most go to 1000, or W1 in this case. We at most go to W. Oh, I did name it T and W instead of A and B. Okay, so I just did A and B to generalize in other problems. Anyways, we only go to W because anything above W is legal anyway. So all the contribution we add to stuff above W, we just give it to W. So that also have to involve we now give contribution to later I's instead of receive contribution from earlier I's. But it does not matter, or J, I guess in this case. But it does not matter. So yeah, Fi plus 1 equals max Fi plus 1, or Fj plus val I. But technically, it should be next instead of I plus 1, because if I plus 1 is greater than, not I plus 1, I plus wi is greater than w, then we just keep cap it at w. If this is greater than or equal to 0, obviously it works, otherwise it doesn't. And when we fractional program, we also have the val is the thing that we calculated above, which is this, ai minus bi times mid. Exact same thing here. Okay. Yeah, initialize fi. Okay. So that is it for this problem. Memorize this algorithm, memorize the solution, or at least memorize this problem number so you know, or memorize this YouTube video. I'm pretty sure, is this allowed? This is not AI, right? It's pre-made online source, but it doesn't really count as simple syntax. So I'm not sure. Look at the USACO rules. See if it's allowed to watch this YouTube video again, if this algorithm actually appears. Because I just have this hunch. Like, look at how hard this algorithm is, and look at what time it's from. There is no way that this thing doesn't reappear. This is such a good algorithm that USACO discovered. Even if they don't use it this year, they're going to use it eventually. And also the fact that it hasn't appeared for the past 6 years only increases that possibility. Anyways, thanks for watching. See you tomorrow. Okay, for the grind report today, I only had 1.5 hours because there's the youth symphony ensemble of a city that I went to today, and I did the strongest friendship group problem, which was from a while ago, contest mocked, and I did actually manage to come up with basically the entire solution because I had all the essential observations and ideas basically, but I made 2 key mistakes. First of all, I tried to use a vector to keep track of every node I had to remove every single time in one run, but we don't need to do that. Like, don't be a sweat, guys. It doesn't have to be that accurate, that precise. If there's a tie, just let it be. Remove them one at a time. So like think through those situations and don't make yourself work harder than you have to. And also I try to consider components independently, which is obviously stupid in a connectivity problem like this. Anyways, yeah, very simple trick of this problem. At first I noticed immediately that for a smaller degree points, we want the largest node possible, largest connected component possible. And then I just realized the only reason we don't want that largest connected component is because, well, the smaller degree nodes. So how to get rid of that? Well, we just remove the smallest degree node every single time. And then I tried to do some goofy stuff, but then I looked at the solution and realized that I made those 2 mistakes. And then just like a 30-minute speed run. Every single time we found the smallest degree node, I did use a set here, which I don't think is necessary, but looking at the solution, I don't really know yet. I'm looking at the solutions code right now and see if that's absolutely necessary to use a set, because after all, that is a red-black balance tree, which no one likes. Oh, priority queue. So this guy used the priority queue. I get it now. Okay. Okay, he used a priority queue. He did some random goofy stuff, but that just proves his algorithm time complexity is exact same as mine. Because, I mean, optimally, you could probably achieve O n alpha, alpha being 4 under a very large number. If you don't know what that is, that's the anti something something function, the time complexity of union find. That doesn't matter. But we did use what's it called? Something something merge. I can't believe I'm just blanking out on these algorithm names. I know the other one is path compression, and this is another optimization. Is it inspirational merge? Something something merge. I gotta search this up. Sorry guys, I am blanking out. Innovative. Oh, heuristic. What? Huh? Is it innovative merge? Oh, DSU on tree or heuristic merge. Okay, I've always just called it innovative merge. Oh, interesting. Anyways, yeah. So we use that and we use path compression. So theoretically, if there's a better implementation than set or priority queue, so we get rid of this log right here, we can achieve n alpha time complexity, which, I mean, that's to be precise, it could just be 4n, since alpha is going to be 4 under, like, I'm pretty sure 10 to the 10 to the 10th power or something like that. Huge number. Anyways, that's just a little absolutism on time complexity that I dumped on you there. But I did do a problem today, which is better than yesterday, and I also did a video, which is also better than yesterday, and I also blanked out on the videos. But it's okay. We have USACO in exactly 4 days. 4 days. Saturday. Good luck to everyone taking it, but I will continue to make video until the last minute, until the last day. Sorry, and hopefully we all get through. We all go to the division we want. Thanks for watching. See you tomorrow.